Hello, everyone. Let me first thank the TQC committee for the opportunity to tell you about our recent series of works on the fundamental limits to general quantum resource purification tasks and their practical applications. The first paper is from 2019 and published, which first put forward the no purification theory. And paper 2 is a more recent follow-up, which completes the picture for channel resource theories and discusses more applications. This is joint work with Kunfeng from Baidu Research. Here is an outline of the content. I will first introduce the most general form of the theory and then talk about a few concrete cases. Our general results are bounds on the accuracy as well as the efficiency for quantum resource purification tasks in both state and channel or static and dynamical settings. We will introduce two different approaches to deriving these bounds. We looked into the applications to a series of practical problems in quantum information processing, including magic state distillation, quantum error correction, circuit synthesis problem, and quantum channel theory. The key problem we would like to address by this work is noise, which is a big obstacle that prevents us from realizing the advantages of large-scale quantum computation and other technologies. This is because quantum systems and quantum information is intrinsically very susceptible to environmental noise effects. Mathematically, the noises generically make the ideally pure quantum systems mixed states, so that certain quantum information might be lost and the quantum systems become unreliable or lose their power. Our community has been developing and improving many methods with the general aim of taming the noise effects or purifying these noisy quantum systems, such as quantum error correction, error mitigation, distillation, and so on. But so far, there's not much systematic understanding about their ultimate performance in practice. And this is what we hope to address. Another notion we need to introduce is the notion of quantum resources. We learn from economics that things acquire resource values when they're useful but hard to attain due to certain constraints. Here in our physical context, practical setups or experimental setups place constraints on what you can easily do to quantum systems. And these constraints induce certain quantum resource features. There are many interesting and important examples in quantum information, like entanglement, which is can be induced by local operations in classical communication, and magic states, which is induced by stabilizer or Clifford group constraints. There is actually a wide variety of different forms of quantum resources that could emerge in different contexts. The manipulation of quantum resources underlies all kinds of quantum information processing tasks, and they can often be understood as the origin of the quantum advantages that we want. Then the so-called quantum resource theory provides a general language or framework to characterize and study the manipulation of different quantum resources. A certain quantum resource theory is defined by the sets of free states and free operations. Here we only care about one golden rule, which is that a free operation must map any free state to another free state. Or in other words, a free operation cannot generate a resource. So in principle, the definitions of these components can be very flexible according to the scenario that you care about. But the point is that any non-trivial set of free operation must be contained in this non-generating set given some set of free states. Because if a free operation is able to generate a resource state, then the theory just becomes trivial. Or in other words, what cannot be done under this condition is considered impossible in all non-trivial theories, or let's say any no-go theorems that we find are considered to be the most general possible. Here we're going to consider this general task of transforming a noisy or a mixed state to some target pure resource state by free operations, maybe probabilistically, and some error could be allowed. As we will further see, many important tasks in practical quantum information processing may take such form. What we will show is that there are universal no-go theorems, or namely lower bounds on the transformation error on such kind of tasks that apply to any well-defined resource theory, for any pure target resource state, and for any free operation or free manipulation. So a key point of our results is that they are very versatile and can be easily adapted to a broad range of problems. Or as another quick recap of the important features of our setup, it concerns the important practical problems of noise, restrictions on the manipulation, and finite resources altogether from a very general standpoint. Now let's see the first proof idea, which can be explained by resource measures. For meaningful resource measures, the most basic property is the monotonicity property, which basically means that the measures should not increase under free operation. That is, a state with a smaller value can never be transformed to a state with a larger value by free operations. Here, our idea is to consider a very special resource monotone induced by this so-called quantum hypothesis testing relative entropy, which is a suitably smooth version of the mean relative entropy. Then the resource measure version of it is given by minimizing over a free states sigma. Then due to the data processing inequality of this quantity, we indeed have a resource monotone. To get some intuition about why this monotone is particularly useful, let's set epsilon to 0. And then the P here becomes the projector onto the support of rho. Then we can easily verify that this monotone is 0 for generic noisy states, but positive for pure non-free states. Then note that the smooth version has good continuity properties. So for small epsilon, the order on the states will preserve, and we can derive lower bounds on the error by analyzing the detailed behaviors of these quantities. With a little tweak of the analysis, we can also deal with the probabilistic case. And the overall result is that it's this forbidden regime of the achievable accuracy and the success probability, which depend on the properties of the noisy input state as well as the target pure state. This forbidden regime is akin to the uncertainty relation. So a conceptual overall message is that perfect resource purification is impossible, even probabilistically. Such error bounds can actually be applied to this more widely studied setting of distillation, where one roughly intends to extract certain high-quality resource states from a larger number of noisy or raw initial states. Now we are interested in the number of copies n needed to achieve some desired accuracy, which characterizes the cost of the distillation protocol. Then our previous error bounds can be translated to bounds on n. And in particular, in the small error limit, we get that n scales at least logarithmically in the inverse error, which is a figure of merit that's of interest in practical scenarios. Here, this is a high-level description of the overhead bound, and we will discuss magic state distillation more specifically later. But now, before introducing the second approach, let's define an important extension of the resource theory framework, where the resource objects are now quantum channels or dynamical quantum resources. And now the manipulation is described by channel-to-channel maps or supermaps. This generalized framework is necessary to discuss, for example, Shannon theory and circuit synthesis problems. And it is under very active study in recent years. Here, in particular, the counterpart of the purification task is to simulate a unitary channel by noisy channels. A key subtlety or complication of the channel theory compared to the state theory is that multiple inputs can now be composed in presumably different inequivalent ways, such as in parallel or sequentially, or even in more complicated ways. So the generalized purification task for channels is now to transform multiple channels that can be consumed in different ways to some unit resource channel by free supermaps, which obey a very similar golden rule of not generating resource channels. Now let's go on to see another way to unravel the no purification phenomena, which is even simpler. It is based on decomposing a noisy input into a probabilistic mixture of a free state and some other state. Then notice that by the golden rule, the free component in the input will actually remain a free component in the output. And therefore, the output cannot be exactly the target pure resource state. More specifically, by quantitatively tracking the process, we can obtain newer error bounds, which mainly depend on the size of the free component. This idea can be adapted to channel theory, where multiple inputs can be used in different ways, as introduced just now, to obtain powerful bounds. More specifically, the bound now depends on the largest size of the free component, or the largest possible P in this expression, instead of the minimum eigenvalue in the previous approach. Furthermore, we can show that this lower bound is tight for certain interesting cases, such as the cubic coherence theory, where there is depolarizing or dephasing noise of any strength, as demonstrated by the diagram here. This method is also discussed in this concurrently posted paper by Regular and Takagi. Now let's see some applications of the above general theory to practical problems. I'll first discuss magic state distillation, which is an important proposal for fault-tolerant quantum computing. The idea is to produce good T states offline and use them to emulate T gates in online computation. These T gates are hard to protect in circuits, but also necessary for achieving universal quantum computation. And magic state distillation is the biggest source of resource cost in such scheme. So understanding the achievable efficiency of magic state distillation is very important. A common formulation of the magic state distillation task is as follows. The input is n copies of noisy magic states rho, and the goal is to output with probability p a state where each of its m marginals is epsilon close to T state. And then the question is how large the overhead n has to be. Now, by refining the two general methods described earlier, we are able to obtain such explicit lower bounds on n. As you can see, n indeed scales at least logarithmically in 1 over epsilon. And the quality of the initial noisy state is encoded in the basis of the logarithm like this. Let's now make some comparison with the efficiency of known magic state distillation protocols. Well, the most studied protocols are based on using stabilizer codes and reiterating the error correction process until reaching some target error. For these protocols, the key parameter characterizing the efficiency is often considered to be the exponent gamma in the average overhead n over m. Then in code language, our lower bounds have two key implications. The first one is that any sub-logarithmic protocol, such as the recent breakthrough one by Hastings and Ha, must have a diverging output size so that the overall cost could blow up. Then also for a large class of codes, for example, the k=1 code, our bounds indicate that the exponent in average overhead indeed has to be lower bounded by 1. Okay, the next interesting application I hope to talk about is quantum error correction, where the encoder and decoder are subject to certain types of constraints. For example, stabilizer quantum error correction is the well-studied case where we have stabilizer or Clifford group constraints. And covariant quantum error correction is the case with symmetry constraints that we shall discuss in a bit more detail in a minute. The key observation here is that such error correction tasks can be formulated also as purification in both state and channel settings, since the goal is to recover the pure logical states or to simulate the identity channel. Here, let's say a bit more about the case of covariant quantum error correction, where the codes are subject to symmetry constraints that the encoding must be covariant with respect to symmetry transformations. There are several strong motivations for studying covariant quantum error correction. For example, the famous Easton-Kneel theorem is closely related, and the covariant quantum error correction plays key roles in, for example, quantum gravity and condensed matter physics, as quantum error correction and symmetries are very central notions in the recent study of these areas. Then, by the insight of treating covariant quantum error correction as a purification problem, we can derive theoretical limits on the accuracy of such quantum error correction tasks using our resource theory methods. Note that here we consider continuous symmetries. The relevant discussions can be found in our second paper, as well as another more extended paper with Cici Zhou and Liang Jiang. In particular, in this paper, we analyzed a specific monotone based on the RLD quantum Fish information, which is also able to induce no purification bounds, and actually works particularly well for this covariant quantum error correction problem. In that paper, we also used quantum metrology or channel estimation theory to derive another set of good bounds. We recently also have a rather strong achievability result, which mainly says that, in fact, a hard random encoding unitary that satisfies charge conservation or U1 covariance almost always saturate the error lower bound to leading order, or in other words, charge conserving unitaries almost always generate nearly optimal U1 covariant codes. This work is featured in another talk at this TQC. So if you're interested in this topic, please also check these papers out. We also discussed how our general theory can be applied to quantum communication or Shannon theory and circuit synthesis problems in this more recent paper. Due to time constraints, I shall only do a brief overview about that. For quantum channel theory, a core problem is to understand the capacities of quantum channels to transmit information. For example, for quantum capacities of noisy channels, we're essentially interested in the optimal rates of simulating identity or unitary channels. So our channel no purification bounds can apply. Then the different types of capacities, such as the normal non-assisted one, or entanglement assisted, or non-signaling assisted capacities, they really just correspond to different supermaps or combs in our unified formulation. And then for circuit synthesis or compiling, the problem is usually to decompose a large unitary that encodes a certain quantum computation or algorithm into a set of elementary components or gates. And we are often just mostly interested in optimizing the number of certain difficult gates, such as T-gate in the Clifford plus T scheme. Here, if we consider a practical version of the problem where the gate is noisy, then our channel no purification bounds can also induce concrete lower bounds on the gate count. For example, this diagram here shows the lower bounds on the noisy T count for approximately synthesizing a CCZ gate. So this is pretty much what I want to talk about here. Thank you for your attention.